are now going to discuss design features of the creel and the drafting unit. As we have already discussed that this machine can be divided into 4 sections: creel section, drafting unit section, twisting section and winding sections. So, we will now first discuss the creel part and the drafting unit part. Creel. The creel consists of a frame with rails running from end to end of the machine, on which bobbin holders are suspended. So, creel is basically a place where the roving bobbins will be mounted. The roving bobbins, as you have all know, they are the feed package. So, each production position of the machine needs to be fed by one roving bobbin, and hence all the feed packages are actually getting stored on the top of the machine. So, the creel is actually placed on the top part of the machine, that is the space which is actually utilized for accommodating all the feed packages of the machine. So, if we have a big machine like 1980 spindles, then that space must be able to occupy 1980 bobbins also. So, the creel has a frame, and the frame there are rails running from one end to other end, and from these rails the bobbin holders are suspended. Bobbin holders are suspended on actually ball bearings. Each spindle has one bobbin holder. You see in the diagram, the actual image shows lot of bobbins hanging. Bobbin holders are also shown, a sketch is shown also in the slide, and there are in the bobbin holder on the top part you have the ball bearings, so that the bobbins can rotate very freely. The purpose is this. We have ring over here as shown, and the retainer, that is some projecting out triangular finger type items are there. These are called retainer. As the ring is pushed with the top end inserted inside the pivot, the retainer swings out to hold the bobbin. So, when you want to hold the bobbin top end is pushed, and then the rings are also pushed up with the top end inserted. The retainer will swing out to hold the bobbin, it will hold the bobbin, and the bobbin will start hanging from the creel, and because the top part is actually there is a ball bearing there, and hence it is easy to pull out roving from the bobbin. If the ring is pushed up again, the retainer is retracted and the bobbin is withdrawn easily. So, that mechanism is there inside this bobbin holder, that in one push of the ring, the retainer will move out and will hold the bobbin, and therefore, bobbin will keep hanging. Another push of the ring, the retainer will move inside and the bobbin can be taken out easily. That is how it is going to work. And other thing is, as you see in the diagram, that all the bobbins are actually hanging from the rail. Now, in the creel design part, what is important is the requirement is that it must accommodate a large number of roving bobbins. How many bobbins? All depends upon the size of the machines. So, machine may be having 1000 spindles, it may be having 1200 spindles or 1980 almost 2000 spindles. So, for each and every spindle we need a feed package. So, we need that many feed packages at least. We may need some more extra which will act as a buffer. So, the whole creel design should be such that it should be able to accommodate a large number of roving bobbins. the design should also be such that it should promote easy unwinding of the roving from the bobbins without any undue stretch. This is very important. See, from the roving, as the roving is pulled out, there is no guiding device. So, from the surface of the bobbin to the drafting unit, this long journey of the roving is without any guidance, without any support, and therefore, every chance that the roving might get undue stretched, and any undue stretch of the roving may lead to long thin place formation in the yarn, which will then therefore affect the quality of the yarn. We have to ensure that the roving is unwound very easily. Another thing is, we have to avoid the interference of the bobbins with each other. So, the bobbins should be placed in such a manner that it should not touch each other. There should be some gap left between them, so that one can put his fingers or hand and remove a bobbin or insert a bobbin, and the bobbin surfaces should not touch each other. At the same time, the height of the creel should not be too high, because it should be accessible to the operator. Ultimately, operator is going to pull out the roving from the bobbin, or he is going to insert a roving bobbin in the creel. Therefore, the height should not be too much, keeping in mind the height of the people who are working there. So, these are the various aspects which the design of the creel must satisfy. Now, bobbin holders are generally arranged in a staggered manner. A arrangement is shown here. What we are interested to know is that how many rows of bobbin rail we should have to accommodate the roving bobbins. Should we have 2 rows, or should we need more number of rows? And second thing is, at what intervals the roving bobbins should be hung. What is the interval at which the roving bobbins should be hung? So, what it is that is going to decide this? This all depends upon basically spindle gauge. What is important here is to know the spindle gauge. What is spindle gauge? Spindle gauge is the distance between the centers of 2 successive spindles, that is the spindle gauge. So, from the point of view of having more and more production position, we should have less and less spindle gauge. If we want to have more number of production position, then we should have less or low value of spindle gauge, but low value of spindle gauge will have other restrictions that we will see now gradually. So, the spindle gauge is distance between the centers of 2 successive spindles. If that distance is g, then we have written here. So, each spindle is surrounded by a ring. So, we see here in the diagram that blue circle indicates the ring, and inside that the small circle indicates the location of the spindle center. Therefore, the ring is much larger than the spindle, because on the spindle the bobbin is going to be inserted, and then bobbin is going to be filled up with yarn. So, if we see carefully on the right hand side diagram, what we are showing by these circles, the first circle, the inner circle represents the tube, that is the bare bobbin, the plastic tube or the bare bobbin, that circle indicates. Then there is a circle shown with this orange color. This is basically circle indicates the full bobbin, when the bobbin gets filled up with yarn. So, that is what it is being shown, and then the blue circle indicates the ring. So, between the full bobbin diameter and the ring diameter there is a little gap, we have to keep an allowance, so that the yarn on the bobbin does not come into contact with the stationary ring, otherwise the yarn will going to be damaged, because the bobbin continuously turns and therefore, the bobbin surface is continuously moving at a high speed. So, we have to always maintain a gap. The biggest diameter of the bobbin should be little less than the diameter of the ring. And then around the blue circle you see another circle, which is the balloon control ring. Now, what is balloon control ring? We will discuss later on as we go through the course. So, that circle indicates the balloon control ring, and then beyond that the final circle is the balloon envelope, that is the diameter of the balloon. So, for each spindle, the diameter of the balloon, the maximum diameter of the balloon indicates the space that the production position needs, and therefore, the space requirement of the production position depends upon the diameter of the balloon that we are going to produce as the loop of yarn revolves around the axis of the bobbin. And hence, as you see here, if we see the ring diameter, which is much less than the diameter of the balloon, and therefore, the distance between successive spindle will be how much? Is going to be G is going to be 2 into dr by 2, where dr is the diameter of the ring, and then there is a gap y. This is basically y1 in this case. Y1 is the allowance between two successive corps to avoid collision between their respective balloons. So, we have to maintain a certain distance between the successive rings, because the size of the ring and the size of the balloons are not exactly same. Balloons are little larger, but if we can reduce the size of the balloon, then we can accommodate more number of spindles. That advantage we have. So, we can say roughly that the gauge, spindle gauge is dr plus y1, or y1 is the little allowance that we keep, so that the two rings do not touch each other also. On the ring the traveler also is running, so therefore, also we need the gap between them. So, that little gap that we required between the two ring is because of the traveler that we have on it also. We have to ensure that the balloon should not collide. So, keeping in mind all these facts, we keep a distance between them, and which we say that the gauge therefore will be the diameter of the ring plus some extra, which is allowance that we keep. Yes.
Allowance will be equal to the balloon envelope for a single balloon or both the balloons?
What we have to see, the two neighboring balloons should not collide. So, that means if whatever is the balloon envelope, the gap has to be little more than this also. Otherwise, there is occasionally they may come into contact with each other. So, to avoid this tendency of balloon colliding each other, what we have nowadays on the machine is balloon separators. So, balloon separators are kept so that under no circumstances the two balloons do not come into contact with each other. If they come into contact with each other, the yarn is going to break, and therefore, what we need is a balloon separator. So, the reasons are these, that why do you need an allowance y1, that is to take care of these aspects. So, the spindle gauge is going to be therefore dr plus some allowance, which is let us say y1. The typical value of G is around 70 to 90 mm, and the values of ring diameter, they may vary and it can be 36, 38, 40, 42, 45, 40, all depends upon the size of the package that you want to make, the count of yarn that you are going to produce. That decides what should be the typical size of the ring diameter. Typical diameters of the ring is typically between 36, 38. These are very, very common. Now, if you have to now see that the way the bobbins are hung, that each roving bobbin should feed each roving bobbin is feeding its own roving to the spindle. So, therefore, spindle to spindle distance, which is G, that is what is the gauge, and the path of the roving from the roving bobbin to the spindle, they should match, so that the roving is aligned with the axis of the spindle. So, alignment is necessary, otherwise the roving has to take an inclined path. We want to avoid that, so that the roving is not get stretched by any means. So, from each, it is best thing would be to make sure that the axis of the bobbin holders and the axis of the spindle gauge, if they match, then that is the best. And therefore, what will happen if we do this, and if I say we use the distance between them is G, then look at the other diagram which is shown here, this diagram. Two bobbins, roving bobbins are shown by the two circles, and one is behind the other. That means, the bobbins are in two rows, but there is a distance between them, that is y2. So, if we place them the way it has shown here, then AB has to be equal to G, where G is the spindle gauge. That means, the way we should hang the roving bobbins one behind the other in such a way that the AB distance should be actually matching the spindle gauge G. If it is true, then we can write that from the triangle ABC, cos beta is AB by AC, that means it is G by AC, and G is the spindle gauge, and how much is AC? AC is diameter of the roving bobbin, that is the full diameter of the roving bobbin, and y2 a gap that we maintain between them, so that they do not touch each other also. So, therefore, we can find out how much should be the cos beta, and also we can find out, if I know the cos beta, then you can find out the tan beta is going to be BC by AG, if you look at from the triangle, and therefore, it is BC by G, and hence BC we can find out, which is G into tan beta. So, we can find out the value of BC, and BC is the distance between the two rails. So, we should, from this we can find out that how much should be the distance between the two rails. This geometrical analysis can actually guide us to find out the distance between two rails where we are going to hang the bobbin holders. And the other thing is, given that y2 is the allowance, so which could be maybe 1 centimeter or so, so that the two full bobbins should never come into contact with each other. So, some gap is necessary, that gap we can keep arbitrary, maybe it is 1 centimeter or so. So, we can find out by from this geometry that what should be the distance between the two rails, that is the value of BC, the center point of the two bobbins or the bobbin holders, that is the point A and point C, also therefore, will be uniquely determined, because AB must be equal to G, and BC can be find out from this equation 4. So, we know where exactly C will be located if we know the position of A. So, once this is decided for 2 bobbins, rest of the bobbins the bobbin holders positions can be easily determined. But once this is fixed for a given machine, because for a given machine the spindle gauge is fixed. So, once the spindle gauge is fixed for a particular machine, the location of the bobbin holders on the bobbin rail also becomes fixed, then they cannot change. All right. From there we complete the discussion on the Creel part of the machine. So, the Creel design wise, function wise, working wise is very simple, but the important aspect of the Creel is that the bobbin should be able to unwind, or the roving should be able to unwind from the bobbin very easily. See, the roving should not get unduly stretched by any means. That is what is the most important part of the Creel part of the machine. We move on to the drafting unit now. The ring frame drafting unit and the speed frame drafting unit, there are a lot of similarities, and we have discussed in more details about the drafting part in general while discussing the speed frame or the roving frame. Now, drafting elements are what? They are the steel made grooved bottom rollers, synthetic rubber cover top rollers, swinging top arm, aprons, apron cradles, roving guide and spacer. These are the various elements of the drafting units. All of them they play their role, and each one of them is important from the point of view of good drafting. Now, main features of the drafting is shown here. It is a 3/3 double apron drafting unit. Top rollers are carried on a pivoted pendulum lever. Aprons are necessary to guide the fibers in the main draft field. So, it is a 2-zone drafting system, back zone and the front zone. The front zone we have the aprons. Front top rollers are slightly forward relative to bottom rollers. So, the way they are placed, they are slightly forward with respect to the bottom rollers, and the middle top rollers is slightly backwardly placed with respect to the middle bottom rollers. So, front top roller is placed slightly forward with respect to the front bottom roller, and middle top roller is placed slightly backward with respect to middle bottom rollers, not back rollers. Back rollers are placed one on top of the other. So, the little offset is there, we call it overhang for the front roller. The purpose of this overhang is to reduce the size of the spinning triangle. So, we will discuss later on what is the importance of spinning triangle and why do you need therefore an overhang of the front top roller over front bottom roller. Apron cradles are equipped with special anti-friction clips at their front edge, which allows apron to run smoothly without buckling. That gives better fiber control. So, if we look at the apron cradles, they are equipped with special anti-friction clips at the front edge. The aprons are passing over the apron cradle, and this apron cradle, there is a friction between the apron and the apron cradle. This friction is a source of resistance to the movement of the apron, and therefore, what we want apron to move smoothly, and therefore, we need to reduce the friction. So, here as you see the apron top and bottom apron this diagram, and it is going over this or this. These are the cradles, top apron cradle is shown, and there is a friction. We have to reduce the friction, and therefore, we have anti-friction clips, or the surface has to be very, very smooth. The idea is that the apron should move smoothly and it should not face much resistance to its movement. Better alignment of top roller relative to the bottom roller is what is required in this case, and leaf spring maintains correct pressure over long time in comparison to coil spring. Here therefore, in the ring spinning drafting unit, leaf springs are used, they are preferred because they maintain a constant pressure or correct pressure over a long period of time. The draft is in between 15 to 70, I mean generally 70 is too high, we keep the draft much less than 70, but theoretically or it can go up to 70, but generally in the practical sense we never go up to 70, we do not even go up to 40 also. We generally keep the draft much less than that, otherwise the quality of the yarn suffers. The top roller pressure is set at these levels 16, 13 and 10 decanewton. So, the pressures are actually different in different rollers. So, that is what about 3/3 drafting system, simple in terms of the number of rollers, the aprons which are there, which are in the front zone, so as to guide the rollers, so guide the fibers, because we know that in ring frame most of the draft is in the front zone, and therefore, the draft is very, very high, possibilities of fiber moving in irregular fashion also is becoming very high, and therefore, what is required is proper guidance, and for this guidance we need aprons. So, what is this guidance means? The guidance basically means that we will ensure that any fiber which is being released from the nip of the middle roller, they start moving at the speed of middle roller only till their forward end reaches the nip of the front roller. That is the purpose of having aprons. Now, we have another type of drafting unit, the arrangement of rollers are shown here, it is called INA drafting. What is special about it? The back bottom roller is placed slightly above the drafting plane made by the nips of the front and middle roller. So, we look at see the drafting plane is shown by this dotted line, that is drafting plane, but the nip of the back pair of rollers is much above this drafting plane as shown over here, and this distance is roughly half roller diameter. So, this distance from here to there is equal to half roller diameter. The back top roller is offset to the rear by about 25 degree. The angle is also shown here in relation to the drafting plane. So, this is how the back pair of rollers are placed. As a result of this, what happens? The roving loops around the back bottom roller as well as apron top roller and remain pressed against the roller, resulting better fiber control in the break draft zone. See, in the ring spinning, we are very much concerned about the fiber control in the back zone. In the back zone, there is no apron, and therefore, there is every possibility that the fibers may move in erratic fashion in the back zone, though the draft is much less, but because the roving is twisted, we are bound to keep the distance between the two roller nips little larger, and therefore, the chances of irregular movement of fibers in the back zone is there, and hence we have to find out ways and means to make sure that the fibers do not move in erratic fashion. So, this kind of arrangement means that from here to there the roving is actually moving over the surface of the bottom roller. So, bottom roller surface itself is actually guiding. So, they are under some frictional control of the bottom roller surface. So, that is what it basically means, and as it enters the middle roller nib, it comes into contact with the middle top roller first and remain pressed against it. So, when the roving is pressed against the surface, the motion transfer from the surface to the fibers becomes better, and therefore, a wrapping of the roving around the roller surface can help to draft the fibers in a better way. So, that control is there. The other thing is the effective distance between the nibs of the middle and the back roller is larger than the fixed roller distance. If we look at this diagram, if I place this roller over here on the top of the bottom roller, the nib to nib distance, if the roller would have been here, the nib to nib distance would be only this much. But by having this, now the distance is from there, it goes up to this point. So, if I put it like this is A, this is the point B, and this is the point C. Earlier it would be AB, but now because the nib has extended backwards, the total effective distance has become AC. So, that is the another advantage we have, that we can keep the nib to nib distance has increased, while the center to center distance of the bottom rollers has not changed. Just because of the placement of the top roller backwards, we are actually extending the nib backwards. From there, another thing about the drafting unit is the roving guide. See, behind the roller there is a roving guide, that the roving, as it moves out of the roving bobbin, finally as it arrives near the back roller, it passes through a roving guide. The guide is placed just behind the back pair of rollers. The guide is given slow oscillation along the width of the roller as shown in the diagram. It is not fixed in one location, it keeps on travelling back and forth. So, some oscillation is given, and the amplitude is slightly less than the width of the roller. And what is the purpose of this oscillation? The oscillation ensures that the roving is drafted by entire surface of the roller and no deep impression is created on the roller surface. If we keep the roving at a fixed location, then the top roller, which is covered by synthetic rubber, will get a permanent impression over there after maybe 1 day, 2 days, maybe after 1 month. So, that particular in that location, the diameter of the roller will be less than the rest of the part, and the wear and tear will be also faster there. So, if we want to spread out the wear and tear, at the same time we want to avoid having any permanent impression of the roller, we need the roving guide to move slowly from one end of the roller to the other end. So, from left hand end to right hand end, it keeps on oscillating. The only thing we have to ensure that while oscillating, it should not go beyond the edge of the rollers. That is what is important. So, oscillation amplitude has to be decided in such a way that it is not going, the roving should not go beyond the edge of the top roller. So, that is the purpose of the roving guide. Now, though the drafting system of ring frame and speed frame are similar in many respects, but then the question may come that what are the differences between them. That is what is also important for us. Otherwise, both are 3/3 roller system, both the machines have drafting units have aprons both on top apron and bottom aprons. So, let us see what are the differences. One is front zone spacer. Ring frame. The ring frame comparatively a small number of individual fibers are involved. See, by the time the fibers are arriving at the front drafting zone, their numbers are very few, because they should be equivalent to the dimension of the yarn. Hence, intensive control has to be exerted by the narrow opening at the apron release point by choosing a spacer having smaller thickness. The same thing if we compare it with the speed frame drafting, interfiber friction due to thicker fiber mass in front zone produces very large effective drag, because the fibers are more in number. How many more in number? Typically they could be 12 times more, 10 to 12 times more in the front zone of speed frame than in the front zone of ring frame, because the total draft is 10 to 12. So, speed frame front zone is a large bunch of fiber is there. So, drag is very high. Therefore, intensive control is not required as it is required in the case of ring frame. Hence, too narrow opening at the apron release point is not required. Therefore, the spacer which is used in speed frame is thicker, or the spacer which is used in ring frame will be thinner. This is the basic difference. It will be because on ring frame I have to handle less number of fibers in the front zone. In the speed frame we have to handle much larger number of fibers. So, that is the difference. The other difference, so here the gap is shown in this diagram, the gap M. The other thing is front zone setting, center to center distance between the bottom rollers. Speed frame front zone setting must be of adequate width to permit an undisturbed drafting operation. Otherwise, the drag may become too strong to overcome by the drawing force of the front pair of rollers, leading to undrafted portions. This is what we have to remember, Kevin. Here more number of fibers are involved, and therefore, drag or drafting force is going to be very high in comparison to what we see in the case of ring spinning. The front zone setting is little closer, therefore, in this case than that is used in speed frame, as mass of fiber is low. So, to reduce the drag in the as mentioned, what we do, we can increase the setting to reduce the drafting force. That is the that is what is done. Therefore, in the case of speed frame, that basically means the front zone setting for the same fiber will be little larger than what we keep in the ring frame. The setting in the case of ring frame will be narrower, while the fibers are exactly same. The other thing is apron to front roller nip setting. So, where the apron ends, from there to the nip of the front roller, there is little gap also is there, because the apron is not really going inside the or close to the nip of the front roller. It cannot go that far. So, the distance between the apron ending point to the front roller nip, that is also important setting point. An increased distance between the apron release point and the front roller nip in ring frame may increase the problem of floating fibers, resulting more irregularity into the yarn. That basically means that this is also an important setting in the case of ring frame, because it can affect the irregularity value of the yarn. In the case of speed frame, this is not so important because number of fibers are more, and therefore, there is a self control due to larger fiber mass. So, this setting, that is apron to front loader nib, apron ending point to front loader nib, is a sensitive setting in the case of ring frame, but is not so sensitive in the case of speed frame. So, all the differences are coming because the mass of fiber is more in speed frame, mass of fiber which we are handling in ring spring is less. The back zone setting, if we compare, back zone setting is low in the comparison to what is kept on speed frame, as roving fiber mass is much less than sliver. In the back zone for speed frame, we are feeding a sliver, so mass of fiber is much larger, and hence back zone setting needs to be wider in the case of speed frame, but back zone setting needs to be narrower in the case of ring frame, because fibers are less. Where the fiber is more, that if you are feeding a sliver, then drag is also more. So, there is no effective control to be exerted there in the rear zone. The purpose of the draft here is to straighten out the fibers in sliver, so as to ensure an even flow of slightly tensioned, well parallelized fibers into the main draft zone. Most of the drafting is performed in the front zone in the case of speed frame. So, there the setting is not really so again important. Obviously, the setting should not be too close to each other. In that case, the fibers may be simultaneously clipped and get stretched. So, otherwise it has to be a little wider than the length of the fiber, but ring frame setting is little less, speed frame setting is little more. All because of the fiber mass that we are going to handle, and this table gives you the kind of setting that we keep for speed frame and ring frame in back zone and front zone, and you will find from this table that whatever I have stated, that while coming to ring frame, the allowance that we keep, see L max is the maximum length of fiber, and the rest is the allowance that we keep it, and that is always less in the case of ring frame in comparison to speed frame. So, this is another difference. So, these are the differences that we find in speed frame and ring spinning drafting systems. Draft and its selection. The draft should be such that it minimizes end breaks and it ensures a good yarn quality. So, breakage is one issue, because more draft sometimes means more irregularity means more breaks. So, how these are how they are connected. So, we cannot give very high draft also. Similarly, the quality of the yarn will suffer, because more imperfections will be generated if the draft is not appropriate to the quality of fiber that we are processing. The critical drafting region for cotton roving is in between 1.3 to 1.7, which is avoided for avoiding stick slip phenomena of fiber movement. This draft is this is the magnitude of draft where the stick slip phenomena may occur in the case of roving. So, where do we keep such kind of draft? The back zone draft is going to fall in this region. Therefore, in ring spinning, the break draft is more critical than the front zone draft. Front zone draft is much higher, where it is much beyond this stick slip zone, and therefore, front zone draft is not so critical, whereas the break draft, how much break draft we are keeping, that becomes very critical issue in spinning operation, because it is this place is somewhere where we have to avoid stick slip phenomena. So, and that will vary from roving to roving, fiber to fiber, twist in the roving. Many factors are there which decides what is the exact value of draft, where stick slip phenomena is going to occur. For synthetic fibers, the critical draft value is slightly more than the cotton. So, this is what we have to keep in mind, and why do you therefore are very much concerned always for the selection of break draft on ring spinning. The total draft is decided by you see so many factors: kind of raw material, composition of raw material, length of fiber, preparation of roving, how the roving has been prepared, how many drop hem passages we have given to the slybird before it was converted into roving, or whether it is a comb roving or not, that is the preparation part of the roving. Roving twist, setting of the break draft zone, thickness of the spacers and hardness of the cord. So many factors are there which will decide the total draft. So, therefore, it is very difficult to say with conviction that this is the draft you must use, but there are certain guidelines based on experience, and people will always start with the guideline and they actually check the yarn and then decide whether it is right or not. Break draft guidelines as available in some textbook is shown here. These are the guidelines for carded cotton and for combed cotton depending upon the total draft. What we generally see here that on an average the combed cotton we can go for slightly higher break draft, because combed cottons have no short fibers and the fibers are much parallel in the case of combed cotton. Whatever entanglement is still left in the fibers will not be there if the fibers are combed. See the carded carded slybird, when it is converted into roving, though this has undergone maybe 2 passages of draw frame, still lot of entanglement will be still present in the fibers in roving. But if the fibers have gone through the combing route, then many of these entanglements have been removed, because as it passes through the comb cylinders, the comb needles will be able to remove most of these entanglements, and also it will be able to remove short fibers. As a result, the roving that we get when you go for combing operation, there it is much better, and hence they are capable to undergo a higher drafting even in the back zone. So, therefore, in the comb bird we see on an average the break draft can be kept slightly more in comparison to what we keep for carded cotton. Only is difference because of the short fibers and the removal of entanglements between fibers. Total draft selection guidelines for different yarn count is shown in this diagram or in this table. First of all, this is from some norms book, and what we see here that one side count is there, the other column is showing the draft that we supposed to keep. So, this is basically a guideline which had been stated. Now, if we put these values on this graph and try to fit a best fit line, then we can see that all these points can be, the trend line can be shown as to be z equal to 8.5 log x minus 8.6. that is this trend of the points on the graph can be described by this empirical equation, where z indicates what? Draft, x indicates count in any. So, z equal to 8.5 ln x minus 8.6, and if we feed this equation, use this equation to predict the corresponding draft, then we get a dart value of 11.07 for tens mixing. For 40s count, we get a value 22.85, where the suggested value is 22, and let us say for hundreds count, suggested value is 30, and the equation gives you a value 30.54. And therefore, we can say that this equation can be used to estimate the draft that we need to produce a yarn of a given count. So, this is a first estimate. So, one can set the machine, spin the yarn, and then test it, and if required, then one can do final adjustment later on. The other thing is the drafting force, which we are going to now discuss. It is the force required to draft the roving that continue sliding of fibers, that is to continue sliding of fibers. Force required to draft the roving. How much force I need to draft the roving? The force is required basically to overcome the frictional resistance to slippage between the sliding fibers. That is why we need force. Drafting force depends upon fiber length, fiber fineness, roving twist, roving count. These are the things which will affect the drafting force. It also will depend upon the moisture content of cotton in the case of cotton, or too much force may lead to emergence of undrafted ends from the roller nip. So, very high force is detrimental, because what will happen? The fibers will simply plucked from the nip, and we call it undrafted portions of the yarn. So, that is how the drafting force should not be too high also. The drafting force versus break draft diagram is shown here, or you can say in the initial part of the drafting, how the drafting force is changing with the draft is shown here. Zone, the whole drafting force, if you see the break draft is this side and the drafting force on the x axis. So, what we see here, that as the draft is increasing from close to 1 to 1.4, the draft force keeps on rising, and then around 1.4 or 1.5 somewhere is suddenly falls. The entire drafting force stress can be divided into 3 parts or 3 zones: zone 1, zone 2, zone 3. Zone 1 is what? Force increases with draft. The draft straightens the fibers in the roving. This is an elastic zone, and the fibers do not yet slip here. So, in this part, the fibers have not really started slipping, only the fibers are orienting along the axis or along the directions of force applications. That is what is happening during this part, and as the fibers gets oriented, there is a reduction in diameter of the roving. So, gripping between the fibers is going to increase. As a result, the structure as a whole is offering more and more resistance to deformation, and that is why there is a rapid rise of force in this particular zone 1. The structure is actually consolidating. That is what is happening here. Then zone 2, as the draft is further increased, the fiber starts partial slippage here now. The static frictional force has still not been overcome, and the force rises with a lesser slope. Zone 2, the slope has changed and maybe partial slippage has started now. Then we go to the zone 3, a point is reached when the force suddenly falls. In zone 3 we see now onwards, because of why it has fallen, slippage of all the fibers have started now in this zone. Suddenly all the fibers in the cross section start slipping. So, as soon as they start slipping, there is a sudden reduction in force. Now onwards, dynamic friction will come into play. It comes, and now onwards this force remains stationary, continues like this, because all the fibers are now sliding and the dynamic coefficient of friction has become now important only. The peak force has been reported to be seen in the breakdown range of 1.4 to 1.6. So, this is around 1.4 to 1.6 somewhere there. The peak force may be seen depending upon, as I said, fiber, its length, its fineness, roving count, roving twist, all these things will affect. So, in zone 2 is basically a zone where stick shift phenomena has just started. This is a destabilizing zone. So, we see the curve like this somewhere here. Actually, some fluctuations is recorded, and therefore, in this zone, if we keep the drop, the movement of the fiber is going to be erratic in nature and any erratic movement is going to produce an irregular yarn finally. Okay. From there, the other thing which is important also is the slippage of aprons and top rollers. The middle bottom roller drive the bottom apron, which in turn drives the top roller. So, drive goes from this roller, bottom roller, to the apron first. This apron gets its drive. Apron in turn drives the top apron, bottom apron drive the top apron then drives the top roller. So, that is how the motion goes. So, bottom roller to bottom apron to top apron to top roller. That is how the motion is transmitted. Now, the bottom apron is pushed forward by the frictional force between the middle bottom roller and this apron, because from here to there is a friction between the bottom apron and the roller surface, bottom roller surface. So, frictional grip is on in this region only and the motion is transferred. Now, the bottom apron, look at this, there is resistance to the movement of the bottom apron. Why? Because friction between bottom apron and the apron guide bar. This is the apron guide bar. So, there is a friction between these roller, so apron and this guide bar. Friction between the tension bracket and the top apron unit. This tension bracket which is here for tensioning the top apron, that also resists movement of the top aprons. Top apron unit as a whole also offering resistance to the movement of the bottom apron, because bottom apron one side is in contact with the top apron, the other side is in contact with the apron guide bar. So, as it wants to move forward, a resistance to its movement is offered by these two, the top apron and the guide bar both, and friction between top and bottom apron also as stated here. So, at so many places the bottom apron is actually receiving opposite forces, and hence what can happen? The only driving force is the grip over this particular zone or zone, let us say zone Q. In this zone only there is some amount of the friction between the middle bottom roller and the apron is actually trying to drive the apron forward. So, the apron is basically pushed forward, not being pulled by the front roller. That is the difference, the way we drive the aprons. In many cases, generally we pull the aprons. Here it is little opposite, that you are not pulling it, but you are actually pushing it from behind and it is going forward. The like let us say conveyors, if you look at the conveyors, they are always pulled by the front pair of rollers. Wherever conveyors are used, there are two set of rollers on which the conveyor is running, but the front pair of front roller, not pair, maybe just a roller, is actually pulling the apron pulling the conveyor forward, and the back one is actually giving support to it. That is all. And you see in the many we have conveyors in blowroom lines, like your inclined lattices which are there. All the lattices are basically a kind of conveyor, and all these lattices are, when they are running, there are two pulleys, one driving pulley and other is driven pulley, and the lattice is placed on them. So, there it is always pulled, but here it is just opposite, it is pushed. So, bottom apron may move slower than the middle bottom roller. See, middle bottom roller is driving the bottom apron, but apron may move slower because the apron receives so much of resistance, and hence it may not be able to move forward, and as a result the top apron may also move slower in response. If the bottom moves slower, top also will move slower, because top gets its motion only from the bottom. High drafting force in the back or the front zone may cause the top roller to move faster. See, if roller 2 and 3 sometimes may move faster if the force here is very high in this zone, as shown in the diagram with the arrow, then it will pull the roller 2. The force is so high, then the roller 2 will be pulled by the roving which is here in the back zone. So, if in the back zone, if the force on the roving, drafting force on the roving is very high, force basically means the drafting force I am talking about, or the tension on the roving which is in between the pair of rollers. If that tension goes very high due to some reason, maybe the twist is too high, or maybe the rollers are too closely spaced, or suddenly the roving count has become heavier. In that case, the drafting force in the back zone may go very high, and as a result what may happen? The roller 2 may start moving at the speed of the roving, and the roller 2 therefore will move faster than its corresponding bottom roller. Similarly, it can happen with the roller 3 also. So, these things sometimes leads to faster movement. So, and that in a way both this apron, therefore, the rollers will slip, because the speed of the two rollers are not exactly same. Whenever the roller speed are not same, we can say it is one is slipping against the other. So, the slippage needs to be avoided always, but if the slips are there, then actually this will all lead to irregularity in the final drafted product, that is the yarn. So, we have to avoid this kind of slippage. The slippage reduction is because by following means: increasing load on top rollers, however it will increase bearing pressure and more energy to run the rollers; increasing wrap angle of aprons on the middle bottom roller; keeping the apron bar free from dust, that is the guiding bar. Reduction in drafting force can also reduce slippage, as an example, increasing length of front drafting zone will reduce the drafting force in the front zone and hence restraining force on aprons and therefore slippage. That is also possible, and reduce the twist on roving, drafting force can reduce, and with this we close this session on drafting. So, we have to see that there is a possibility of slippage also in the case of drafting aprons. The other thing that we have discussed is the how much draft we should keep, what are the various factors which affect the selection of draft, then what should be the draft distribution, importance of break draft, the stick slip phenomena, and the role of your roving guide, why they are given oscillating motion, all such things we have discussed. And with this, let us close today's session. Thank you.